start the recording on my local machine. And I think anytime, Margaret, that you want to go ahead and start, we're probably good to do that.
Thanks, Pete. Hi, everyone. Welcome to the CIMSS Flash Talk Social, the only one of the spring. Happy St. Patrick's Day. About a year ago, we started doing these because, as you know, we were abruptly barred from the building. And many of us were feeling pretty isolated. So we thought, oh, let's just try these informal talks, see what people are working on, get to see each other, get to hear from each other. So we did a bunch last year, and then AOS was willing to host us late last fall. So we got to use this slot a couple times. And now again, AOS is helping us out. So I want to thank Pete, and I want to thank Gerald. And I also want to thank our 4 colleagues today that are presenting, because we have what I think a pretty amazing lineup. We've got GOES, we've got VIIRS, we've got the new CSPP, if I'm saying that correctly, Dave can correct me. And we also have a social science talk that I think sounds pretty interesting that Ian is going to give us today. So the current lineup has John, then Eva, then Dave, then Ian, and I'll let you guys introduce yourself, and I'll monitor the chat. Thank you very much, John. Take it away.
Yeah, thanks, Margaret. So I'm John Cintineo, a researcher at CIMSS. I want to acknowledge Mike Pavlonis, the PI on this project from NOAA, and also Justin Sigleff, another researcher at CIMSS who has also done a lot of work on this project. So I'm going to be talking about using the GOES Advanced Baseline Imager and Deep Learning to nowcast lightning occurrence. All right, use this arrow to advance. Okay, so we all know that lightning is hazardous for aviation and mariners and outdoor events and activities. So here we're trying to use ABI only to nowcast lightning occurrence in an accurate and timely fashion. So you guys probably all know geostationary imagers cover large swaths of real estate over our planet and can provide really good high frequency updates. The data can provide observations of clouds prior to electrification, potentially increasing the lead time to lightning strikes. And the current GOES series of satellites also provides an optical lightning imager with the geostationary lightning mapper. Okay. Oops. Okay. All right, good. So forecasters often look at images of satellite data to predict lightning in the short term. So the model we're proposing is a convolutional neural network, or CNN, and I'll talk more details on that in the following slides. But in general, CNNs are really adept at finding salient or important spatial features in images for prediction or detection problems. The domain of interest is the Southeast US, I call it offshore region, since the main impetus of this project was to initially predict lightning where there's little or no radar data. The predictors channels are from the ABI visible and IR channels. And the target metric is this GLM flash extent density. What that is, well, I'll get to that in a minute, but it's accumulated over 60 minutes from a given current time and binarized at one flash. So it's either there is lightning or there isn't lightning. So, okay, the training data are from May through August of 2018. Validation data and testing data are also from those months, but we divide it up by date segment. So basically, the training data is like the first 14 days of the month and the last 10 days of the month. The validation data is 15th through 19th of each month. Oh, sorry, the test data is from 2020, so completely independent set. So the flash extent density is this gridded product that can, how do you say, like unwrap the parent-child relationships among GLM flashes, groups, and events. So it kind of depicts how many flashes can traverse a given pixel. Okay, so I guess I would binarize the flashes at one flash per unit time. So it's a binary classification problem. Okay, CNN is similar to a feed-forward neural network, except it carries the assumption that the inputs are images, and the neurons in a given layer of a model are connected only to the adjacent layers in a specified spatial neighborhood. So the neurons in the input layer, so the first layer in our model, are pixels in the image or a data array. So our model has 4 input channels: the 0.64 micron reflectance, the 1.6 micron reflectance, 10.3 and 12.3 micron brightness temperatures from ABI. And the output is the probability of any lightning within the next 60 minutes. At every pixel, we generate a probability. And it's in cloud or cloud to ground, since our target truth data can't easily distinguish between cloud to ground or in-cloud lightning. So we're using a popular architecture to produce predictions at every point. This is generally referred to as a U-net. The upsampling layers and skip connections and concatenations help maintain better spatial resolution to final output grid of probabilities. And the number of feature maps per layer, which is indicated by the white values shown under each block. Number of feature maps per layer, number of convolutions per block, and the number of convolution pooling blocks themselves were tested in an iterative way, attempting to maximize the critical success index on the validation set. Okay. So I'm going to start by showing a bunch of examples. Let me explain these first. So given a set of input data arrays, and obviously probabilities at each horizontal pixel, so it's straightforward to contour these and overlay them on top of satellite imagery. So the probabilities, or the contours, are probabilities of lightning in the next 60 minutes. So as I play the animations, you'll also see these blobs of GLM flash extent density. They'll mainly be bluish purple. And these are valid for the scan time only. So it's not exactly what it was trained on, which is the next 60 minutes. So the model makes these predictions or inferences very fast. It takes about 30 seconds to complete a CONUS-wide image, and 3 seconds to complete a mesoscale scan image, which is about, I think, 1,000 kilometers by 1,000 kilometers. And this is using about 20 CPUs simultaneously. So our prediction is not using GPUs, but it was trained using GPU. Okay, so there we go. So we have some boundary here off the coast of the mid-Atlantic US, spawning some morning thunderstorms. And the model generally predicts higher probabilities before the first flashes occur. And I think the predictions correspond, play it again, fairly well to where a forecaster might expect lightning in the near future. Right, go on to the next example. So we were pretty encouraged by our initial results of predictions in the offshore region, so we decided to run the model over land as well, see how it does there. So this is a cold front over Iowa. Some cells develop quickly while others develop flashes more slowly. But again, in general, the model does a nice job of isolating regions along the front that have enhanced lightning potential. Come on, there we go. Okay, so here's another movie, a cold front in Tennessee with more complex overlapping cloud cover. The model still targets the regions of potential lightning activity fairly well. Play it again. So, there's mid cloud, high cloud, of course, low cloud, but it's still, that's pretty good with very few false alarms regions. So this is another more complicated scene in Western New York. There's there'll be I think a lake breeze boundary here. And despite the rapid growth, there's still about 10 minutes of lead time from the 50% threshold to the initial flashes. Okay, so in this one, the GLM extent density is semi-transparent. So there's a lot going on. I'll play it twice, but want you to focus on the Florida Peninsula and the developing convection there. Probability of lightning occurs, or the contours seem to match pretty well with different stages of convective development, and it often correctly highlights the soon-to-be electrified regions. So when I say it corresponds to different stages, well, so when you have just some really small Q, the probabilities will be lower. As you have some towering Q, the probabilities will be higher. So it corresponds well to our conceptual model. So another movie from Florida, an offshore region. So I think the model captures convective development both over land and sea, with a fairly low amount of false alarm regions and lead time in many regions. Not every region, and you know there's still misses and everything, but for a pretty complex scene and different cloud types, it does reasonably well, I think. Let this run through again. Okay. So again, the GLM flash extent density is semi-transparent here. So you'll particularly see this ramp up of probabilities in Pennsylvania and elsewhere as air mass becomes unstable. So even though the model wasn't trained on this region at all, it does a pretty good job of picking up these bubbling Q areas that are likely to have lightning. So I think it's the last example at a much higher satellite viewing angle over the Intermountain West. So there's numerous storms forming on different orographical features with the daytime heating. This is a very common occurrence in the summertime out there. So again, a very different satellite viewing angle than what the model is trained on, but it captures the potential lightning features fairly well. So these next few slides we're just going to discuss the performance of the model in mostly a bulk sense. So we sample, or sorry, wrong slide. No, that's right. Okay, we broke down our data set into day, night, and combined. So we chose a solar zenith angle of, I think, 88 degrees. The attributes diagram, so this is the one on the left, it shows some very good reliability or calibration of the probabilities. You want your lines to be on that 1-to-1 line, which is, it's kind of obscured because these lines are right on there. So what that means is that your forecasts are occurring at the rate of your events, which in our case is the occurrence of lightning flashes in the next 60 minutes. So the nighttime only predictions, the blue line, show a little over forecasting bias above the 50% threshold, but in general, predictions are pretty well calibrated. And oh, I guess I should talk about the test data set a little bit more. So yeah, I think I said it was like 5 days, May through August of 2020, 5 days each month. So we sampled every other pixel in X and Y space just to save some time. But even with that, there were over 220 million pixel predictions. And okay, so now the performance diagram on the right shows the probability of detection versus the success ratio, or 1 minus a false alarm ratio, for different probability thresholds, where we use those probability thresholds to binarize the probabilities, or basically binarize the predictions of 0 and 1. And from this, these blue contours are the critical success index, which is basically model accuracy, but neglecting correct nulls or false negatives, since most of those for this type of problem are pretty trivial. So the values in the circles represent the probability thresholds. And we can see that daytime predictions are better than nighttime here. Most likely owing to the fact that daytime you have the visible reflected bands. But in general, overall, the model does pretty good day and night. The most skillful threshold was about 32% probability, and the CSI is about 0.5. So the critical aspect of performance is also lead time. So especially for lightning initiation events. So we want to correctly predict lightning before it occurs. So to do this, we place these valid patches approximately every 80 kilometers. This is just one method of doing it. And for a given patch P at a given time, T naught, if there is no lightning present within P at T's, etc. So we're not counting, we're not taking scores in this method, this analysis, and a corresponding GLM data at 5-minute temporal resolution. The data are discretized. That's why you see some of these. So if lightning occurred during the 60-minute period, the lead time minutes prior, since we don't know when exactly in that 5-minute interval the flash actually shows, you can see the median lead time is about 12.5 minutes. However, there's a pretty hefty tail toward greater lead times for most of these thresholds. So recall at this threshold that half of the hits generate lead time between 7.5 and 27.5 minutes, whereas 25% of the hits have a lead time greater than 30 minutes. So, if you don't get lead time for every convective cloud, but for a number of clouds, you get appreciable lead time. So I think that's pretty promising. All right, so just to wrap up here, we trained CNN to predict lightning up to 60 minutes to the future at any given point using 4 reflective or absorption channels on ABI. And ABI alone can provide pretty skillful short-term prediction for lightning, day and night over land and sea. And lead time often ranges in the range of 10 to 30 minutes for a lot of convective clouds. This can hypothetically be used in domains with a geostationary imager similar to what we have on ABI. And in the future, we want to, what we're doing now basically is bolstering our training data seasonally and geographically. We want to do some relevance analysis for predictors to kind of get at the physical reasoning of what the model is learning. And for an operational perspective, we may add radar over land, which should enhance predictions over land as well. And that is all I have. So thank you. Happy to take any questions.
Thanks, John. We have time for one quick question, and Tim already typed it in the chat. And he asked whether if you use more IR info at night would help the nighttime performance. He gives the example of water vapor difference with an IR window.
Yeah, so we've looked a little bit. We have some tests with some IR or some water vapor channels. Didn't seem to affect things a whole lot in terms of skill. I think using more data geographically and seasonally, then the water vapor channels will help. So I think that's another thing we should probably take a look at with more diverse data. Yeah, good question.
All right, thanks. And you and Tim can talk more about that. All right. I think you need to stop sharing.
Yep, thanks.
Thank you very much. Well, I do see another question in the chat for you, so maybe you could answer it in the chat. I can see your screen. Okay.
Yeah. Can I start?
Yes.
Yeah, so my name is Eva Borbas, and I am a senior scientist at the CIMSS. I am mostly working on two areas, if the infrared moisture and the land surface emissivity determination. Today, I will talk about the moisture study, and I will talk mostly about the, sorry, this is not my first slides.
I think you need to use the little arrow in the bottom. Oh, there you go.
Yeah, here it is. Okay, sorry about that. So I'm trying to go back to the first one. Yeah, so I will talk about our effort to improve the VIIRS moisture retrieval using the VIIRS+Cris data fusion product. And the colleagues who are working on the same topic with me is Elizabeth Weiss, Chris Moeller, Brian Baum, Paul Mansell, and also Jeff Curtin and Ethan Nelson from the atmospheric SIPs helping with the data processing. So motivation is to work toward continuity of moisture product from the Terra and Aqua MODIS, what we already have for 20 years, and in the future, satellites like SUMI-NPP, NOAA-20, and subsequent GPSS platform with instruments. But we have a big challenge that the VIIRS imager doesn't have a water vapor and CO2 absorption band. So this really limits our capability to determine the tropospheric moisture, especially upper tropospheric humidity. So to demonstrate that, here I plotted the spectral response function of the MODIS bands, what we are using for the MODIS moisture retrievals. As you see that there are two bands in the water vapor absorption band. We have ozone and CO2 bands. And here you go is the free VIIRS infrared window band, what we can use. The M15 and M16 is 11 and 12 micron because split window bands can be used to determine moisture, but mostly on the lower part of the troposphere. So just a general idea about the MODIS moisture products, what I'm talking to, and then what we want to have a continuation from VIIRS is this official name is Atmospheric Profile Products. And this is a clear sky retriever over land and ocean day and night. It's a 5 kilometer resolution product, so that's kind of an advantage of the product. We have calculated outputs of the total precipitable water, which is the integration of the full column of water vapor. And we also provide 3 layers of water vapor, the low, mid, and the high layers, total ozone, temperature, humidity profiles, and stability indexes. So we also have a VIIRS operational product available at the NASA DAC, and that's based on also the similar, sorry, I missed that. I just wanted to say that this algorithm using statistical regression, and then we regress the calculated 11 band MODIS bands, brightness, temperature against the atmospheric profiles. And then generally our product, so I will focus on the TPW, the moisture part, and we can say the uncertainty is about 2.5 millimeter, what we determine over the quartzite handily picked over 300 clear sky cases compared to the microwave water vapor, which considered the most accurate water vapor determination instruments. So for the VIIRS, we are using the same statistical regression algorithm, but instead of using the 11 band, we are using only the free available window bands from VIIRS. Plus, we added the Nowcast TPW, and we constrain we calculate a regression between that and the atmospheric profile. We use the Nowcast TPW. So the Nowcast is the CRIS and ATM sounding retrievals, which provide total precipitable water as an output to. We use this to constrain the TPW magnitude over a pixel, what we determined previously with a VIIRS split window bands. This panel shows some example of daily and monthly mean product. But what I want to focus on this table on the right side, when we calculated similar statistics over the SGP site, and then you can see when we use the VIIRS only channels, then the RMS is almost 8 millimeter, and the Nowcast is helping to constrain down to 4.9 millimeter RMS error. So this product, because we only have information from the lower level of the moisture in the atmosphere, provides outputs only TPW, but we provide both the VIIRS only and the VIIRS plus Nowcast. This is our two official products. And then came the opportunity when the VIIRS+Cris fusion radiances became available. So the VIIRS+Cris fusion radiances is calculated for the MODIS bands. So from now I will call like MODIS-like radiances, and then taking information from the CIMSS sounder instruments, but provide the data on the imager spatial resolution. This panel shows here some image comparison between the middle panels is the constructed fusion radiances for the MODIS band, and the right is the MODIS radiances. But I want to focus on the right panel, the top one, which is the comparison between VIIRS fusion and MODIS brightness temperature for the two water vapor band. Each dot is represent over 10,000 collocations. And as you can see, you can get the accuracy is less than half a Kelvin for the two bands. So we took this opportunity to use this MODIS-like radiances, and then we created our new VIIRS products. We called it the VIIRS Fusion products. And that's what we plan to propose as a replacement of our version 1. And we use exactly the same algorithm as we use for the MODIS on the 11 bands, but this time is the MODIS-like constructed band from the VIIRS+Cris instruments. And as you see that, because of the same band information, we were able to create the same outputs as the MODIS has. So we are bringing these moisture products in a family with the MODIS. For evaluation, we compare daily and monthly mean product between the fusion MODIS and the VIIRS operational product. This figure shows example for April 9, 2018. The top left panel, A panel, shows the MODIS TPW field. Bottom below is fusion, VIIRS only, and the VIIRS plus Nowcast products. And then the right side is the corresponding differences. So between fusion MODIS, VIIRS only MODIS, and VIIRS plus Nowcast MODIS. So as you see that the fusion TPW is the best fit to the MODIS with a negative 0.3 bias and 3.3 RMS error. I'm not showing here, but we got very similar results for the monthly comparison. We selected 4 months representing the 4 seasons. I'm showing here the latitudinal distribution for the same day for the 4 products. The top is the TPW binned in 1 degree zones, and the corresponding differences, the number of observation. And then I'm focused over the tropics because that's the highest moisture level when it occurs. So you could see the VIIRS only is really overestimate the MODIS, while the fusion is the closest fit, and the VIIRS Nowcast is a little bit underestimate for the MODIS product. Okay, I mentioned that the official VIIRS product doesn't include upper tropospheric humidity just because the VIIRS doesn't have information about that. But with the fusion, now we are able to calculate that. And then here we compared to the MODIS, the same one-day comparison and the zonal mean comparison, and also for the 4 season. And then I don't want to go in details, but overall we can say that the MODIS and the fusion agrees in 10%. which we believe that it's accurate enough to determine seasonal and daily variation. So to check the whole SUMI-NPP and NOAA 20 VIIRS missions, so the time series has been plotted here for 3 latitude bands. Those are the monthly mean TPWs. The 3 latitude bands is the blue is the tropic between a 30 south and north latitude band. And the green is the northern mid-latitude between the 30 and 60 latitude band. And the red is the southern mid-latitude band. So the differences is hard to see. So below plotted the differences. The first difference plot here is the operational VIIRS product. Particularly, this is the VIIRS plus Nowcast product. And you can see there are bigger seasonal changes, and the differences is between the 2 millimeter plus minus range. And then the bottom 2 is the fusion product, SUMI-NPP and NOAA 20. And unfortunately, on 2018 September, the official VIIRS product has been terminated because of the CRIS and ATMS product change, and we were not able to do the software update. But we are planning to propose to replace that product with a fusion one. In the SUMI-NPP, you are seeing that there is a data gap that's due to the CRIS midwave instrument outage, but the NOAA 20 can cover that data gap. And also very noticeable that the seasonal changes in the fusion data between the comparing to MODIS is much less, and then the differences is between 1 millimeter. So we were very happy with the results, and then we found that the fusion TPW matches the MODIS product with a better bias and RMS than the official VIIRS product what we have. And then we were able to calculate fusion upper tropospheric humidity, which we find that it's a good agreement with the MODIS within 10%. And also using the fusion bands, we were able to calculate all the outputs what we have for MODIS. So we are getting into the family with MODIS. And just as a very summary conclusion, that this finding demonstrated that the potential in use of the fusion absorption band is generating moisture product and continue the moisture record from MODIS and other previous polar orbiting satellites. All of our results has been also published. So here's a reference. The top is the moisture, VIIRS moisture product improvement by the fusion. A second, a similar study with a cloud retrievals. And the bottom is just this explanation of the fusion product. Thank you.
Thanks, Ava. That was great. Great results, too. So we have one question from Jordan. He says, what do you suspect is the cause of the seasonal signature of the seasonal VIIRS+Cris differences compared to MODIS that you showed on the third to the last slide?
Yeah, that's something that we need to further investigate. That's our first results.
All right. Thank you. Thank you very much for presenting.
Yeah, thank you.
All right. So let me know if you can't see this, but I'll just start going. My name is David Hoese. I'm a software developer. When we're not in a pandemic, you can find me on the 6th floor. This presentation is about CSPP GeoSphere. This is a website for showing low latency interactive ABI imagery using cloud deployment technologies. I gave this presentation originally at AMS in January. It has not changed much since then. So if you saw that, I'm sorry. The original mission for this project, the main goal was to get GO16 ABI imagery in front of web users as quickly as possible. We wanted to start with GOES rebroadcast, or GRB, which is really the rawest data stream that we have access to for GOES-R data, and do some processing, get it to image tiles, and get it into users' browsers as fast as possible. We wanted to use the high quality imagery that we create with the CSPP Geo-to-Grid software. We wanted it to be low latency, so as soon as we get all the data from the satellite, get it to your screen as quickly as possible. We wanted to also produce that imagery in the highest spatial resolution possible. So for ABI, that's 500 meters per pixel. We wanted the underlying technology that we use to allow us to deploy this application in multiple environments, whether that be self-hosted servers at the SSEC or some commercial cloud product like Amazon Web Services or Google Cloud Platform. But we also needed to do all this work on a budget. So we only had 2 developers, me working on the back end and Clayton Saplinski working on the front end website part of it. We also only had money for a single server at the SSEC. So the idea of doing a ton of processing on a huge cluster was not something that was originally budgeted. We also had some money to do some testing on Google Cloud Platform. The website that we generated needed to do basic user interaction stuff like panning, zooming, animating through time steps. And then kind of the umbrella goal of this whole project was to learn stuff about these cloud technologies that we wanted to use, but also about how they might be applied to other projects, not just this project and the software we're using, and also the learn about the software involved in generating these image tiles and producing a website like this. So in the rest of this talk, I'm going to talk about the website, the look and feel of it, what features it has. I'll talk about the backend, what technologies we used, and why I think those technologies provide us some flexibility. And then I'll quickly go over some of the decisions we had to make, the pros and cons of those decisions, and where we see GeoSphere going in the future. So the website. This was created with internal SSEC funding. It has a simple interface. That was one of our main goals, is we didn't want to clutter the screen too much. Even in the screenshot here, the menu on the left can be hidden so that you have even more space. It does the basic pan zoom, animating through time steps. You can display multiple times. You can display multiple products, which I'll talk about in a little bit. Multiple sectors, like ABI has full disk, CONUS, mesoscale 1, mesoscale 2. You can also, we wanted to be able to allow users to share their current view with other people, their coworkers, their friends. So you can share a URL and somebody can be looking at the same thing you're looking at. And then lastly, really important, was a auto reload feature, so that if you are, if you have this enabled and new data comes on the server, it automatically gets loaded onto your screen. Here's a screenshot of a zoomed in area of a true color RGB in GeoSphere. And this is really meant to show the high resolution imagery. You can really see a lot of the features of the clouds and the land, just what's available from this imagery. If it doesn't look good in Zoom, I'm sorry, it looks good on my screen. Multiple sectors, so we have full disk, which is what that screenshot before 2 slides ago was showing. This is CONUS. You can also see that this is a true color RGB, but on the night side of the image, we have a night microphysics RGB. I'll show another example of that in a little bit. So that was CONUS. This is mesoscale 1, mesoscale 2. You can choose all of these different sectors to look at. We provide grayscale images for all of the 16 channels that ABI offers. So I think this is channel 1 or channel 2, and then this is channel 14, I think. Just an example of what those look like. There's an info page on the website that tells you what GeoSphere is all about, and it includes a link to the Geo-to-Grid software and how Geo-to-Grid makes these images. It also has a link to a contact form if you want to give us any feedback or questions. There's a sharing dialogue, like I talked about before, with getting a URL that you can give to other people so that they can look at the same thing you're looking at. You can choose specific times that you want to look at. They don't have to be continuous. If you wanted to look at an image for every hour, on the half hour, or at the 30-minute mark, then you could do that. And then hopefully this video loads. So this is showing an animation we saw as tiles come in and GeoSphere finishes loading all the frames. It will start playing the animation. On the night side, we have the night microphysics RGB. And then as the sun comes out, you have the true color RGB on the day side. You can also choose, instead of a normal forward animation, you can have a rocking animation, which I know people at the SSCC, CIMSS, AOS like to look at. You can also control the frames per second. So if you have a lot of frames, then you can look at a lot of frames more quickly. So that's it for the website. For the backend, the cloud portion of this was jointly funded through SSCC and NOAA. All of the CSPP Geo software that we use was developed at CIMSS under NOAA funding. So that's the CSPP Geo GRB processing, as well as the Geo2Grid software. We wanted this backend to be cloud friendly. That meant using some of the technologies on the right hand of the slide, things like Kubernetes, Helm charts, and Docker containers. And being cloud friendly means that we could deploy it on servers at the SSCC or out on Google Cloud Platform or Amazon Web Services. Using these technologies, we were able to produce something that was flexible and configurable, so we can control what types of products are created, what sectors we're ingesting if we need to turn some on or off, or configure our data retention, so how many times are actually available. These technologies make our system pretty robust, in my opinion, because, for example, Kubernetes, if it detects that something is failing or crashing, it will automatically restart it and keep track of that. These components are reusable. So if we want to, each piece of this is its own individual component. So if we want to take that component, configure it a little differently, and deploy it again, we can do that. We have automated deployment and testing configured. So every time we make a change, it's tested and then automatically goes out to the production website. We have monitoring and alerts. So things like how much CPU we're using, how much memory usage, anything that goes wrong, we get a notification about it. And then also I mentioned low latency before. So for a full disk image from the point where we get the last bit of data from the satellite, it takes about 5 minutes in the best case to get a true color image on your screen. Here's a screenshot of the some of our continuous integration automated testing going out. So each of these checkboxes is a test or a deployment of some piece of this GeoSphere infrastructure onto the servers at the SSCC. I can reuse these components without any code duplication, or as little as possible, I suppose. And this here is showing a similar situation, but I'm testing things on Google Cloud. We have monitoring, like I mentioned, so we get all these pretty graphs to keep track of how things are running. When things go wrong, we get a Slack notification. So here's a Slack message with all of the details that we need to go and start debugging this. So that's the back end, the decisions. There are a lot of decisions that have to be made with any application of this size, but then when you start throwing in the cloud technologies that we wanted to use, it just kind of explodes with the amount that you have to think about. So I don't think I have time to talk about every one of these things, but I would like to point out that one of the big decisions was, do we host this application at SSCC or out on some cloud vendor? And we ended up going with the SSCC route just because of the infrastructure we have at the SSCC with our TC group and with the data centers that we have. The lessons learned from doing all of this, first is that the learning curve is huge. Kubernetes and Helm charts are just, there's so much to learn. And then there's so many options for all of these technologies. And then you go on Google Cloud or Amazon and they have their own way of doing things. It's all using the same technology, but how you use that technology is all different. So with all of those things to learn, it's hard to do things the right way or whatever people think is the right way, because you're kind of just trying to get this to work as quickly as possible. And then cloud technologies like these are moving really fast. So you might get something to work, and then a month later you go and read the documentation and they say, oh, well, this is actually not the preferred way of doing this anymore. You should use this other method. Another lesson learned is that traditional methods don't always translate one-to-one to cloud things like this. An example being that if you have software components that might expect to read from a directory, then write to another directory, and then another component reads that output, those things don't necessarily work just out of the box. There's extra things that you have to take care of before those things can happen, and a whole mess of decisions involved with that. There are lots of storage options. When you're working on like just a regular normal server, you might just have a directory that you use. But with all of these cloud technologies, there's S3 buckets, there's solid state disks, there's how do you want those to connect to things? How do you want them to be read only or write only? All of those types of decisions. So after all of that complaining, is the extra complexity worth it? I would still say yes. There's so much flexibility and so much that the software is trying to do for you that for an application of this size, it was just, I think it was the right decision. Looking forward, for GeoSphere, we want to have more automation, try to find those best practices, more documentation, more features like maybe Go 17 or being able to save an animation as you're playing it. And there are a ton of optimizations we could make. The website is public. You can go to it at geosphere.sscc.wisc.edu. If you want to learn more about the CSPP Geo software that's involved, you can go to cims.sscc. And that talk that's mentioned there, that was Kathy Strabela's talk at AMS. You can probably find it on YouTube. And if you want to contact me, you can email me, find that on the SSCC website, or I'm on Twitter too. Thank you.
Thanks, Dave. That was great. I have to say, just from social media, it's also already a very popular product. So there's 2 questions in the chat, and I'm going to ask you to answer them in the chat because we've only officially got 10 minutes left, and I'm going to let Ian start his talk. But thank you very much for presenting.
Thank you.
Ian, you can just, yeah, Ian, you can upload when you're ready. Share your screen, I mean.
Thank you. Let me see if I can get this to work here.
I know you can. And I'll just say, I apologize to Ian already in the email, but we found a way to misspell his name twice, both in the flyer and in the email today. So thanks for still presenting.
Hopefully you can see my presentation here.
We can see it and then we can hear you.
Okay, fantastic. So thanks everyone for attending today. I want to discuss my project on public attention to NWS Twitter information. I've recently started looking into doing this, and I'm going to present a little bit of the pilot analysis that I've been doing. So the background here is that NWS uses Twitter as a supplemental information dissemination channel, but it's also potentially the source of observations, and that for some people it might be more than just a supplemental information channel. So it's useful and interesting to figure out what people are looking at on Twitter from NWS accounts, what gets their attention, what gets people engaged. For example, like today in Alabama, NWS Birmingham's blowing up with a lot of tornado information. So figuring out how to be more effective with conveying that information and getting more attention is definitely the background and motivation behind this work. So some of the goals that I'm looking at specifically are getting into how do people respond to NWS tweets, figuring out what gets attention and what doesn't get attention on those tweets, who are the people who are engaging with these tweets, and I have a goal to build a tool so a potential tweet could be fed into it, and then it would say, this is the likelihood of this tweet getting some attention. And ultimately, the goal is to increase engagement and the ability of these NWS, particularly NWS WFO Twitter accounts, the Weather Forecast Office's Twitter accounts specifically, so not the national ones or the hurricane centers per se. At this stage, give them more ability and understanding of what's getting engagement and how they can crank up engagement in their accounts. In particular, I want to be able to, as a measure for attention, predict tweet favorite count. So when you like hit the heart button on Twitter, if you're familiar with that, that's a favorite. I'm going to see if we can predict that for tweets from NWS Milwaukee. And I'm choosing NWS Milwaukee because they're just down the road, and it's a good starting point for some of this work. So here is Milwaukee account. I'm looking at roughly the last year of tweets, and this is just a count of tweets per day over that last year. You can see the mean is generally 5, medians 4 tweets per day, and you see it can get pretty spiky. Some days peaking up to over 30, 40 up there. I think that's Memorial Day. That's peaking over 40 people interested in the weather forecast for Memorial Day to a high degree there. So they're active every day, but there are spikes and reductions in the activity that they're tweeting. But there's no day that there are 0 tweets, or maybe one day with zero tweets on it there. So it's pretty regular tweeting from NWS Milwaukee, so that's good. But how are people reacting to these tweets? Here's a plot of per tweet favorites versus retweets. This is a log chart here, so you can see it's highly skewed to the bottom left there. Generally, tweets don't get that much attention as measured through favorites or retweets. I'm just going to move pretty quickly through this given the time. Same information again as 2 separate histograms just to show how quickly that drop off occurs. You can see once you get to about 10 retweets or favorites, the numbers are dropping off precipitously there, from thousands down to hundreds. So the underlying message is highly engaged tweets are quite rare, and low engaged tweets are much more common. So what does a highly engaging tweet look like? You might be able to see in the favorites there, out at nearly 1,000, there's one little solitary point there. What does that tweet look like? Here's what that tweet is. So from earlier this year, February 7th, here is a video from in front of the radome in Milwaukee. I'll just quickly play this video. So this was a very, very engaging tweet for NWS Milwaukee. Nearly 1,000 people liked this. This is a very impactful way to talk about some science. So this is the kind of thing that is getting a lot of engagement, but there are also tweets that get no favorites. So here's an example of one of those. This is a text only a little bit of information. No one's particularly excited about this. So maybe this is an example of something that's maybe necessary, but it isn't getting a lot of likes. I wonder if that's also true for retweets, which is another method of looking at attention. Here's a 0 retweets tweet. They're replying to the submission of an observation, which got some likes. So this is good that it got likes, but it's probably the people who submitted the observation that are liking it. So my takeaway from this is that favorites are more sensitive than retweets for attention. Favorites are a little bit more sensitive, but retweets are going to indicate a little bit more robust attention. So here's a heaps of retweets. This is the maximum retweets from NWS Milwaukee, and it's summarizing the derecho from last year. This was a retweet from the NWS Chicago account, actually, but you can see there's some detail in the text here and a very engaging image, and obviously a high impact weather event to go along with it. So this is the kind of thing that's getting a lot of engagement. And this is the kind of thing that I would like to be able to predict. So in terms of trying to predict attention, I need to get those tweets from the last year and try and pull out numerical features that are associated with those tweets that could be then fed to some kind of machine learning classifier that could take those numerical features and determine if there is going to be many or few attention signals. So let's have a quick look at what that looks like. This is a correlation matrix of some features for all of those tweets. These are numerical features such as the positivity or the negativity of the text in the tweet, the length of the text, if there are images, if there are URLs. Going across the top there, you can see the favorite count is correlated pretty strongly with retweets. but it's not strongly correlated with anything else, which is a little bit ominous, but maybe you might expect that with just a small number of basic tweet features that are coming out of the tweets themselves. If I segment this down into just high impact, like 10 favorites or more, we see like a different pattern here. But overall, things are kind of the same in terms of favorite correlations. So maybe it's better to look at a class rather than a regression of, can I predict how many favorites specifically? So I'll just split the tweets into two classes of high impact and low impact. High impact is 10 favorites or more, and low impact is less than 10. So that gives me two classes, and the high impact is around half the size of the low impact. This isn't good to feed to a classifier because it should have balanced classes to make better predictions. So I just resample the high impact class to bring it up to the same count as the low impact. And then I feed that to a regression classifier. And this is the quick result from it, just using some basic settings. You can see the true labels on the y-axis and the predicted labels on the x-axis. And you can see when the true label is 0, low impact, the classifier is having a hard time telling that from whether it's a low impact or a high impact. It's 289 low, 210 high. So it's roughly 50-50 on that. That seems a little random, which isn't so great. But for the high impact class, the true label, when it's always 1 there, the predicted label is getting that right maybe 2/3 of the time compared to 1/3 of the time predicting it incorrectly. So maybe that's not the greatest performance for a classifier out of the box, but there's a lot more work to do here. And that will include extracting more features from the tweets, maybe including some temporal components like season, time of day, solar time, pulling in non-Twitter account data such as ambient weather conditions, and also doing some model tuning and using different models as well. Thank you very much for your attention.
Thanks, Ian. Thanks for speeding it up too. That was great of you. Nice of you.
You're
So
welcome.
we have a comment, I think, from Scott. Whoops, I lost it. Okay. Scott Lindstrom, it's my understanding that particular forecasters at WFOs are designated tweeters. Do you account for that kind of thing when you investigate this? The person in charge of tweets might be working at odd times when followers are asleep. Well, Scott, they work rotating shifts. Sorry, maybe another way to ask this is, are tweets evenly distributed time-wise throughout the day? Oh, sorry, should have read your whole thing. All right.
I mean, those are great ideas, and I definitely want to just reinforce that there's lots of potential other features underlying the data that can influence public attention, and I'm going to have to take some of those into account. So I think that's a great thing to highlight, Scott, and I definitely am going to follow through on that.
So I just have one question. Are you going to share this with NWS Milwaukee?
Actually, this work was sparked from a conversation with a forecaster at NWS Milwaukee who was speculating about what the use of tweeting was or how effective it was in general. And I would like to share that directly. And I suspect there will be a little bit more work behind this before it goes into anything official. Yeah, that's the plan.
Right. You don't want to like let them on to you what you're doing yet. I don't know. It's been a study.
Well, we'll see how informative we can be.
All right. Well, thanks so much for presenting. Thanks everyone for attending. I suspect and hope that we'll wander to the 8th floor in the fall for these talks.